All right, sweet. Alan, would you mind just giving a brief little intro on yourself, a little background, and then we can just rock and roll?
Yeah, absolutely. So I'm currently writing up my thesis based at the University of Surrey in the UK. So it's my doctoral thesis where we're primarily focused on timing of food intake and the interaction between circadian rhythms and behavioral patterns. And then outside of that, I run a website called Alinea Nutrition, which is a nutrition science education hub platform where it's focused on kind of research review. We have a weekly research review and then kind of video lectures and webinars. And then I'm also the chief research officer for Sigma Nutrition, Danny Lennon's platform. And we record kind of bi-monthly podcasts and we produce these kind of written statements as well. So I have a lot of kind of public engagement in nutrition and nutrition science, as well as my own personal research. So I'm kind of looking forward to the journal club. I run one for Alinea. I think they're really useful tools. And I guess I'd encourage anyone to be as interactive with this as you can, or as you're comfortable being. But since there's a nice kind of small group of us, I think we can get something, really productive out of this. And, if nutrition is not your specialty and you're kind of looking at some of the methods and some of this, none of that matters because we can clarify anything. So yeah, looking forward to this.
Sweet. Which paper would you prefer to start with? Have a preference?
No preference. I guess just because epidemiology with nutrition can be a subject that gets a lot of flack, gets strawmanned a lot. Maybe we might start with the plant-centered diet one, and then move on to the salt one.
Perfect.
Yeah, if that works.
Yeah.
Okay, so I guess first question is, has everyone had a chance to read the paper? Awesome. Oh, great. This is excellent. Okay. Before we kick off, so I have a few kind of questions that I use to kind of help us like work through the paper, and I'll ask them as prompts, and you can just like jump in with the answer or any thoughts that you have. But before we do that, any kind of general impressions of the paper, like in kind of broad summary terms?
I thought it made some large leaps. That we're talking that this diet does all these things and that they're making these, they always say associated with, right? But they're almost basically saying it's a causative thing. If I eat plants, then I lower your cardiovascular disease risk rate. But I didn't see that they well controlled for activity, for a lot of other factors that come into that. They mentioned a little bit about it, but I didn't see that they actually showed that their cohorts were things or their grouping was that they were following, that they really took it in. They had some questionnaires that they did, but I don't know the validity of those questionnaires, right? And I'll be honest, I didn't go look and see how well they were, and that they're all based off of somebody reporting. And I don't know about the nutritional literature, but ours, that's not necessarily the greatest method. What did you eat a month ago? Well, I think I ate what I'm going to tell you, fish and vegetables and some of this other kind of stuff, right? But I could have had 6 beers and a whole lot of other shit that I'm just not going to tell you, or I'm not going to necessarily remember or want to remember from that night, right? So I wasn't real clear that we had great clarity that they could make any associations or assumptions other than just looking at these correlative type of things, yet they almost try to make a causative statement in there occasionally that this supports this. And I just thought that they were making leaps of faith.
Okay. So we'll get into diet assessment methods when we kind of work our way through the paper, because that is really valid. And it is one of the main kind of questions people have with nutritional epidemiology is how can we know? And so just the first thing I would say as a broad principle is you're never really looking for a specific day, or, you know, what did you have on this day? The tools that are used are generally based around frequency, which actually people are slightly better at. So although you might not specifically remember what you had for dinner last Sunday, if I asked you, you know, because people tend to be creatures of habits, how frequently do you have oats, or how frequently do you have a banana? People are better at actually having some sort of kind of accuracy with those kind of concepts. But what they did with this study, which makes it slightly more less prone to some of those variables, is they used a score. They used an actual diet score. So with a diet score, you're not interested in any specific food as the exposure. You're not interested in, like, is this, you know, a relationship between fiber and cardiovascular disease? And so this is actually quite useful for epidemiology, because you're actually accounting for some of these potential confounders or some of these inaccuracies by getting a broad characterization of someone's diet and turning it into a numeric score, and then looking at, so you've got like a high adherence score or a low adherence score. And that gives a little bit more room to maneuver in terms of the method of assessing diet and how accurate it can be. So these are known as a priori indices, and you can really kind of, it's a way of scoring the healthfulness of a dietary pattern. So what they're looking to do is actually capture a representation of the total dietary pattern, rather than really specific characteristics of the diet, a macronutrient level or micronutrient level. So it's a much broader exposure of interest. And that's quite useful for these kind of observational studies. And so you would generally, now there are subjective assessments that go into any score. So you would have foods that are associated with health are generally scored positively, and foods that are associated with risk are scored negatively. And then you sum these scores together for people's intake and come up with a numeric representation of the healthfulness of their diet. So it could be that you have 10 food groups and they've 10 points each for a maximum score. And you have people scored out of 100, you know, because of that. If you've 10 food, each 10 points for a maximum score. And these are useful tools for epidemiology. So I just say that at the start, like what they did here in terms of quantifying diet wasn't really looking for any specific, like, I ate this on this day. It was actually looking to get a broader characterization of their diet scored, and then relate that to the outcome of interest. But yeah, we'll come back to the outcome thing and the kind of like associations and factors that are controlled for, or sorry, adjusted for, because we're dealing with epidemiology. Yeah. Anyone else kind of broad thoughts at the start?
All right, I'll go. All right. So I thought, as far as just like from the statistical analysis side of thing, I was like, I'm punching way above my weight here. So a lot of that stuff I got a little lost in. But then I feel like, yeah, in a study like this, one, it's amazing how many participants there were, and for doing it for so long is really fucking amazing. Like,
yeah.
So with a certain study like this, I know you can't necessarily draw conclusions, you know, based on, like, it's not trying to put together like a causative with an outcome. And so there's always like the idea of like, well, okay, if you're able to, there's a lot of confounding variables there. Like you even talk about like maybe a food desert or something like that, where people have a lot of other things going on in their life, maybe lower socioeconomic in there as well. But I think like such a broad swath of like participants, and for so long, I thought it was kind of crazy just like how they were able to put something together like this and have meaningful outcomes by the end of it.
Right. And so this actually relates somewhat to the point just made about potential, what we would call measurement error in the tools you're using to assess any exposure or any outcome. With nutrition, particularly with measuring diet, we know what the direction of the measurement error is. There's been extensive research over 50 years trying to actually capture the size of the error and understand how accurate or inaccurate various methods of assessing diet are. And so what helps you overcome that is your sample size. The bigger the study that you have, the more you average out those errors so that the curve of those errors is kind of flattened a little bit. And you don't really have this highly prone small study where if there's errors within that, it would swing the results either way. So for nutritional epidemiology, the actual, the methodological rigor of the study is boosted the more that you actually increase the number of participants. But interestingly, this study isn't even really that big for some of the major nutrition cohorts. Sort of like the EPIC study in Europe, for example, has over over 100,000 participants. One of the US cohorts, the retired persons cohort, National Institutes of Health, had 500,000 people, so you're really allowing for some of that measurement error to be kind of like dampened a little bit. But
Alan, have you ever seen MSK research?
Have I seen which? MSK
research, musculoskeletal research. We're used to seeing a large cohort of like 40.
Okay.
That's why we're like, wow, these numbers are huge. And you're like, yeah, they're not really not that big. No.
Right. Okay.
They're significantly impressive to us. We don't have large groupings, unfortunately.
Right. Thanks for that, Paul. That context really helps. But I think, Kevin, to your point about the statistical analysis, I have we will work through that because it's a really important point, and like I'll share my screen with the paper so we can go through it. But yeah, look, we'll start working through it anyway, and I'll kind of like throw these questions out and jump in as you need it. But so the one I always start with is, what's the research question being addressed in this study, and what's the main hypothesis?
Yep. So the main question is a shift in diet trend towards, based off this score, higher quality foods. Does that have an impact on like cardiovascular events or disease, which is kind of clustered as like stroke, hypertension, a whole litany of things. Is there even a trend there?
Exactly. And the main hypothesis then framed as, a higher score would be hypothesized to associate with a higher positive score, hypothesized to associate with lower risk of cardiovascular disease outcomes. So, and we've kind of, in answering that, then you've also answered like the primary outcomes of the study, where obviously cardiovascular disease as a composite endpoint. So they called it incident cardiovascular disease, and this is actually important for any really epidemiological study, because incident cardiovascular disease will cover any event for the most part, but you can have incidents and you can have then fatal cardiovascular disease as well. So you can have a death from cardiovascular disease, and sometimes studies kind of mix both fatal and incidents of cardiovascular disease, or of whatever the outcome is, into like total cardiovascular disease, for example. And that can often be just something that's important to think about, because certain diet disease associations might have actually a stronger relationship with incidence of disease than they do with, fatal, or vice versa. They might have a stronger association with actual fatal endpoints rather than just incidence. And then within the incidence, it's like, okay, if you've got stroke or myocardial infarction, a heart attack, it's also important to kind of think about them. We've seen this with some of the research on omega-3 fatty acid supplementation for heart disease, because people have said, there's no effect. But total composite endpoints, there's often no effect. But if you look specifically at heart attacks, there's a massive reduction in risk. So I think it's always important to just think about being granular with what our outcome is. And okay, if there wasn't an effect on the primary kind of composite endpoint, was there potentially an effect in some of the individual endpoints if they publish that data? It's just something to think about generally. Okay, so next question then, what are the participant characteristics and the size, setting, and duration of the study? There's kind of 4 parts there: participant characteristics, the study, setting of the study, and duration of the study. Anyone want to jump in on that?
Size 5,115. Yep. Setting 4 different US cities. And then timeline was 32 years. Yeah, as over that time period. Did any of the baseline characteristics factoring in the US population, did any of the baseline characteristics strike you as like positive or interesting, or was there anything you kind of thought, oh, this is maybe good? Or
I thought it was interesting that they tried to control for like familial history, or at least like record that, like if you had, just from basically not discrediting like the genetic impact to some of these outcomes. So I thought that was like one of the first things that sort of jumped to my mind. Like, would they control for that? And they kind of did try to address it.
Yeah. I mean, you're not going to necessarily wipe out entirely, the potential for a genetic predisposition, but certainly accounting for family history is a positive. And like, the Cardia study has been quite thorough in its kind of baseline, assessment of characteristics within the participants. One of the interesting things, if you look at like the major US nutrition cohorts, the Nurses' Health Study, the Health Professionals Follow-Up Study, they're the 2 longest running. Even the National Institutes of Health Retired Person Study. I mean, the NHS and the HFPS are basically 99% Caucasian, which is not representative of the American population. And what was really interesting about this study in particular was the percentage of female participants was essentially nearly half in total, and the percentage of Black participants. So I thought this was one of the real strengths of the kind of the participant characteristics in the Cardia study, is particularly for cardiovascular disease, because there are like differences in terms of ethnicity that relate to cardiovascular risk, particularly things like hypertension. So I just thought it was really good that this study appeared to be a bit more representative. I'm obviously, even at the percentage, is probably over-representative, but just generally a kind of positive of the study, that it had way more inclusion of Black participants and of female participants than some of the other cohorts. Although the Nurses' Health Study is all nurses, so it's all women. But generally, it's just kind of a bit more representative overall, even for the size of the study. In terms of so we have this kind of, the other thing in terms of the characteristics is, and this was specifically as part of the study, and Kevin, you had mentioned this kind of like time course idea, this shift in diet, is the participants were quite young at baseline. Like average age was what, kind of between, 20, 23, 24, 25. And that's, a lot of cohorts that are established take people who are maybe 50 at baseline or 55. And yeah, while you can adjust for factors, you're often taking people who are already, they may be free from disease,
as in an overdiagnosis. So we're told, okay, they don't have diabetes at baseline, they don't have cardiovascular disease, but we know that these diseases actually have a long, kind of history of development before diagnosis. So they might not have an overt diagnosis, but that doesn't mean that there hasn't been the steps laid for a diagnosis prior to that. So this study's got, young, otherwise, healthy participants at baseline at an age where a lot of cohorts don't actually have people represented in their kind of mid to late 20s, and then following them up over this time period. So I thought that was a kind of nice aspect of the characteristics of the cohort. Okay, so we've kind of covered those, like we know what's being looked at, the hypothesis and the size and the characteristics and the outcomes, obviously cardiovascular disease. There are some more epidemiological specific things that are questions that I have, but before we get there, let's kind of go through the primary results. So what are the main outcomes in terms of the relationship between this plant-based diet score and cardiovascular disease? Does anyone want to jump in on that?
All right, I'll go. So they used, I think it was incidence cardiovascular disease as the outcome. And it was basically you had, I'm botching it. I think it was like a 57% decrease in, nope, I'm botching it. I thought an interesting thing in the outcome.
It was.
Go for it.
I'll tell you what, I'm just going to, Chris, can you allow me to share my screen, and I'll just pull the paper up and we can actually look at the table for the results and we can kind of talk through this together.
Yep, you're good.
Awesome. Cool. Right, everyone can see this? Okay. So this is the table with the results. And so Kevin, I think what you were describing then was basically this. So it was a 56% relative risk reduction in the group with the highest score compared to the group with the lowest score. And the confidence intervals, which are always important to look at, 0.32 to 0.93. So actually quite wide. And even though that indicates that the direction of effect was all toward reduced risk, it does indicate that there's a lack of precision in that estimate, right? When confidence intervals are quite wide, it will tend to indicate to us, because to calculate confidence intervals, you have to include the standard deviation and error and also your sample size. So you're reflecting your sample size and the variability in your measurement. And that goes into calculating confidence intervals. So where they're quite wide, that always kind of says, okay, there's a little bit of imprecision, even though the direction of effect is quite clear. And so that's one thing that I would always, when you're looking at nutrition epidemiology studies, one thing I'll always, and I emphasize this all the time with the website, like when we do a journal club, is I'm always getting people to think about confidence intervals and the point estimate. But as a principle, this is a very common methodological approach for nutritional epidemiology, because, and this comes back to at the start when we were discussing the, how accurate is assessing diet. Well, because we know that there are inaccuracies, we're not trying to get an exact quantification of we're comparing exact amount X with exact amount Y. So what you do is you take the estimate of your intake and you kind of divide it into levels of intake. So really and we know what the direction of the error is, which tends to underestimate intake. So by doing this, you're kind of giving yourself a little more leeway, basically. We're not actually saying this is an exact quantification, that this score is the exact score versus this exact score. We're saying, okay, if we divide people into levels, then we compare the levels. So, and it's very common to divide that level into 5 levels, right, to allow for some of this scope. And then the most common approach, will be to divide the highest compared to the lowest. So this is allowing a degree of leeway. We're not saying this is 100% accurate, but we're saying if I compare people within the assessment we've done in our group who have the highest level of intake of X, whatever that is, versus the very lowest, then what do we see compared to that? And so obviously what they've done here is take a score, right? So it's a numeric score and compared the highest to the lowest. And the lowest score is the reference category, right? So we're assuming that the lowest score, i.e. the lowest adherence to any sort of kind of plant-centric diet, is the reference, and then we're comparing these other reference categories to it. And then when we get that comparison between highest and lowest, then I think it's always good to then look at, okay, what's our point estimate, which is the one here, that's not in brackets. So that's our actual relative risk or hazard ratio, which in this case is a point, you subtract 0.54 from 1.00, because 1.00 is always the null, the no association. And that's where you get your percentage from. So in this case, we've got like a 46% relative risk reduction. And then in brackets, then we have our confidence interval where we can say, okay, the direction of effect is clear, like higher compared to lower is associated with lower risk of CVD. But we can say that, okay, that's quite wide. So it's not a precise estimate. And I'll come back to that point in terms of why it may not be precise as an estimate.
Hey, Alan.
Yeah.
Just looking at that graph, this is one of those parts where my eyes just glazed over. And I felt a little overwhelmed. So that was super helpful laying that out. So, these different groups, they're all being controlled back. They're being compared back to like the reference, which is the lowest score. And then with the models on the side. So that is basically like,
yes,
they're controlling for like subsets, or they're taking into account comorbidities or like different, what they've acknowledged as like confounding variables, maybe.
Exactly. And this is what I wanted to get to, because this really comes back to what we were discussing about at the start. How, okay, it's observational, you've got these potential confounders or effect modifiers. How do we account for that? And the answer to that is multivariate statistical adjustment models. And any good cohort study, any good work of epidemiology will have well thought through adjustment models. And it is common for them to publish the results from each model, right? So at baseline, they'll tend to look at just what they call the raw comparison between high and low. And then what you can see here is model one, then they adjust for the age of the participants at year 0, so at baseline, sex, race, total energy intake, and maximal educational attainment. And that's starting to factor in. So educational attainment is one of the big potential confounders related to socioeconomic status, because higher education tends to correlate with higher income, then correlate with better access to healthy diet and this kind of thing. And then model 2 then is everything that was in model 1 plus parental history of cardiovascular disease, smoking status at baseline, and physical activity level. And then you have model 3, which would be called the fully adjusted model. And that's model 1 and model 2 plus comorbidities, hypertension, diabetes, dyslipidemia, so high cholesterol, and body mass index. And so these are really important. Like, your statistical adjustment models are really important. Now, what you may be thinking, and you don't see here, is, oh, but they didn't maybe adjust for dietary variables. That's because they use this score. So where you use a score, you're characterizing the total diet into a score. You've inherently accounted for potential confounding because you're not actually interested in food A versus food B or nutrient A versus nutrient B. So if this study was looking, for example, at dietary fiber and cardiovascular disease, then you would want to see that they also adjusted for, you know, you've inherently captured the fact that someone smoked before. You know, just because you do a statistical adjustment doesn't mean that person didn't smoke 20 a day, but you're looking for the effect of that exposure across your whole cohort on the outcome. So basically, you're taking each of these in turn. You've got your basic association, and you're running every one of these against your outcome to see whether that association becomes insignificant. And if one of these suddenly made your association insignificant, then you would know that actually that was the confounder. And so a famous example of this from the early 90s, an analysis came out showing that coffee was associated with heart disease, high coffee consumption. And then this pretty smart, awesome epidemiologist at UCLA came along and said, well, hold on a minute. The coffee drinkers were all high smokers. So he then did an analysis, because the previous study hadn't factored in this. So he then did an analysis where, yes, the coffee was associated with heart disease, but once he adjusted for cigarette smoking, then that association was no longer significant, which actually then indicates, no, it was the smoking that was more appropriately related. So what I always encourage people to think about is look at the small print here, because looking at what they adjusted for is going to allow you slightly more confidence that the association, if it survives this adjustment and it's still significant, statistically significant, then, you know, it's gone through, shall we say, the kind of the gamut of these adjustments and still come out the other side. So at that point, then it's worth taking as a valid association. It is, of course, not a causal, direction of effect, but it is an association.
Hey, Alan, going back to how we're utilizing a score, right? The nutrition score as a thing.
Sure.
So that's where we really need to look at how they're grading and how they're breaking out that diet, right? That's why they chose how they chose what food groups, because I really love that they loved beer, alcohol, and wine, and that was in the positive association for health. So that's good for me.
Yeah.
But just looking at
a lot of diet scores do.
I mean, but that's where we kind of have to look there to see what are we including or how are we leaning, because that's an implicit bias almost of, I could choose, well, my top cohort, I included really fat beef because I like it. And I did some of these other kind of things. And then that would screw any of these generalized associations of things, right? I mean, we have to be clear that we have to look and see what they included. I mean, they did include some low fat cheeses and yogurt and stuff of some dairy stuff, but most of this was vegetables and those kind of things in this their top list, right? And then most of their stuff was fatty and sugary on the very bottom list. And then we had some other things just in the neutral. So we have to kind of look at that to make sure that it is actually, their score is showing what they're trying to show as directionality as well, right?
Exactly. And so one of the things about using a score, and I've seen people kind of, when this study came out, start making claims about specific foods, and it's like, no, we need to be really clear that when a score is being used, we can't make any inference about any specific food or food group within that score, right? The foods themselves and those food groups have been used to calculate the score. But by using the score, we're deliberately saying, well, actually, we're not really interested in whether it's the high versus low cheese intake, or whether it's people who drank more wine compared to low wine drinkers. So we're by using a score, you're conceding that actually it's just a representation of total diet, but you're not able to make any conclusions in relation to which foods specifically within what was beneficially rated or otherwise. And there's pros and cons to this. The pro is that it's flexible, right? My diet's not the same as your diet's not the same as Kevin's diet, right? So what you're allowing for is that kind of inter-individual variability in diet. You're basically saying, we're interested in your total diet quality, but I'm not really, you know, I don't care if you drink wine and I drink beer, and, you know, someone eats low-fat yogurt and someone eats cheese. So we're giving up that level of kind of granularity to get a more realistic representation of diet as people eat it in the real world. But it means that you can't make any assumption that, oh, it must have been the salmon they were eating, right? So there's no conclusions we can make about any specific
I'm
food
still
or
taking
food
it
group.
that beer, wine, liquor, and coffee are healthy. That's the way I'm
right. That's it. Yeah, absolutely. Yeah. The data on coffee is pretty clear. So, but yeah, I think, you know, this is one of the benefits of using a score, is because of that. So for this study, you know, for any epidemiological study, what I would kind of encourage you to look at is, you know, what's the reference group? So what group are we being compared to, and what are those characteristics? You know, what dietary assessment method did they use? We're obviously discussing this a lot. And then what adjustment models did they use? You know, what did they consider as potential confounders? Because we know that things like physical activity or, you know, sleep or any of these variables can be important. And then think about the summary estimate of effect. So our actual relative risk, and then our confidence intervals, like how confident are we in the result? And so what you can see here is for the primary outcome was cardiovascular disease, CVD up here. You can see for coronary heart disease, it was not statistically significant. And there's nothing really we can tell from this, because if you look at the confidence interval, it goes from 0.30, which is a reduction in risk, to 1.25, which is almost, you know, literally a 100-point difference. And because it goes over 1.0, you know, this is going from low risk to suddenly high risk. There's no direction of effect we can really look at here. And then hypertension-related cardiovascular disease, 50% reduction in risk, but again, imprecise estimate. So just to wrap this one up, why might the results be imprecise in the estimate? Well, because there weren't really a lot of deaths. That's the thing about this study. So the cohort studies in nutrition are best when there's loads of people and loads of deaths. And this study actually, if you look at it, well, deaths or incident endpoints, this study actually only had 289 cases over 32 years. That's not a lot. And that reflects the fact that they're young at baseline. If they were 50 at baseline, we'd have more events, because cardiovascular disease events, we know, just stratify by age. So because they were young and healthy at baseline, there weren't actually a lot of heart disease, of cardiovascular disease cases. And so that is something that when you don't have a lot of statistical power now to detect associations, because you have to remember that these 289 cases are then being divided up amongst your 5 groups, within which we're looking then at, you know, how many people in each group had, you know, some form of cardiovascular event. And actually, if you look here, then you can see, well, it was 13 out of 992 in the top quintile, 22 out of 1,016 in the fourth, 31. So we're talking about, you know, 37 in this group, only 37, you know, incident cardiovascular heart disease in this case, versus 13. It's not a particularly, I know that maybe for musculoskeletal research, this could be a lot of people, but, you know, it's not providing a lot of statistical power to detect some of these associations. So that's another thing I would kind of encourage you to take home as a note for reading cohort studies in nutrition is, you know, the more of an outcome that happens, the better it is for the analysis. And that tends to be something that we would see then in tighter confidence intervals. We'll just conscious of, we've got the salt one to go through. Was that helpful? Is there any kind of lingering questions people have?
I have a question.
Anything?
Alan.
Yeah, sure.
The models where they're kind of layered on top of each other. Let's say you find a major discrepancy when comparing like model 1 to model 2. From there, how do you differentiate between like those factors within the specific model? Do you just have to do deeper like analysis?
Yeah, you basically do a regression sensitivity analysis where you just go one by one. So if model 2 wiped out the association, you would know that it wasn't any of your model 1 factors, but then you'd go, okay, is it parental history of cardiovascular disease or smoking? And you would basically just regress them one by one on your outcome until you weeded out which one was the kind of major confounder.
Alan, in your world, how do you know how they're, I mean, I didn't see it in there other than they just kind of did some asking of questions, how they're controlling to know or understanding their physical activity levels, their other kind of thing. Because I know we have large error in just even self-reported physical activity measures, right? And most people can't get to our recommended 150, minutes of exercise in a week. What kind of thresholds are they using to do that? I mean, did they break that out? Do you guys look at that specifically as to those risk factors and how they're doing that?
Yeah. So generally, it is obviously a really important, factor. It depends on the study. Cardia has been quite robust in the sense that it's also conducted like repeated measurements over time in its individuals. The physical activity I've just highlighted here you can see, is measured in exercise units based on intensity and frequency, based on, and so because this is not the first publication from Cardia, often what will happen is you'll see a reference here. You can see the kind of superscript 20. So they're referring to the previous research. And often if you really wanted to dig in to the
that's
measure,
where they go through that method. All right.
Yeah.
That's what
you really wanted to, yeah. So you've often got to go to like a big study like this will often have published a methods paper specifically detailing the methods that they've used for quantifying whatever it is, whether it's physical activity or diet or whatever. And then in this paper, they're kind of giving you the very basic kind of detail because they've done it they've published it previously. So when you go down to
well, that explains to me why it just seems like they just kind of mentioned, oh, we controlled for that. And I'm like, well, how did you control for that? Because that could, we're magnifying error on top of error if I don't understand things.
Right. So here's the reference here. So validity and reliability of short physical activity history, Cardia in the Minnesota Heart Health Program. So that's from the Cardia study. And so you will always want to see, and it's such a good point though, because I do this, with any cohort study I'm reading, if they've mentioned the validity of their dietary assessment method, for example, they say we used a validated food frequency questionnaire. I'll go and find the validation study and read the validation study to make sure I'm comfortable with the actual validation process itself. So yeah, with a paper like this that's coming out, Cardia has been going since the late 80s. With a paper like this, they'll just tend to refer to their previous work to save on word space, and you'll just get a very light sense of the detail they've run, which can obviously give the impression that they've kind of just glossed over it. But actually, they're just not duplicating their work, and they're sending you out to read more. All right, I will stop sharing this. And okay, so if we're happy with that, and that was helpful, we'll get on to the salt substitution paper. And this was a really, really cool study, and it's pretty hot off the shelf, like end of last month. So yeah, everyone's also had a chance to read this. Any kind of we'll start with like general ideas or kind of thoughts on the paper.
This is, I think, Paul, you kind of alluded to it in the first paper, but it may be more apparent in this one with whether or not these individuals were actually utilizing the
the salt substitutes for this prolonged period of time, or if they said they were. That was my biggest thought throughout this, of were these groups that were in that in that group, were they actually utilizing it, or were they just using regular salt?
Sure. And so one of the kind of really helpful, robust things about the study, given its size, was the fact that they actually measured urinary sodium and potassium output, which gives you more of an indication of that level of compliance. Because if they were just using regular salt, you just wouldn't see a difference in their urinary sodium and potassium output relative to baseline, and certainly relative to the control group. So yeah, in the absence of that kind of biochemical analysis, I would have been just like, well, how do we know, how do we know they didn't start eating more vegetables, or something along those lines. But yeah, thankfully they did, and they did repeated measures of that over time. We could get bogged down in that. Measuring sodium and potassium in urine is itself like a rabbit hole. It's one of the reasons why there are these apparent inconsistencies in the research on sodium and heart disease. The reason is that our sodium excretion varies from day to day, from person to person. It also varies based on the time of day that you measure. So but on the flip side, you basically excrete the vast majority of your sodium in urine, right? There's some loss in sweat, which is relevant for athletes, but for the general population, it's not a big source of sodium excretion, and there's minimal in feces. What this means is that if you do urinary collections the right way, you can get a really accurate measure of sodium intake. The problem is the number of measurements needed level of accuracy. You would have to, the most accurate study to date was in 1984. And to get a full sample, you need to collect all of the urine that you pass in a 24-hour period. And they had people do this for 28 days. Basically, for a month, people pissed into jars every single day for the whole day. And they managed to measure their urinary sodium intake with an accuracy of like 70 to 80%. If you only do one sodium measurement, even if it's only one 24-hour full collection, you start to introduce a huge amount of measurement error. If you only do a spot collection where they just show up at a certain time of day, you've got even more measurement error. So the minimum to try and knock some of this measurement error back is about three full 24-hour collections repeated in the same person over time allows you to correct for some of that error. Now, in this study, they did the repeated measures, but the annoying thing is that they said from which. So for me, I'm kind of like, okay, the change in urinary sodium and potassium excretion is sufficient to be confident that the intervention group did at least comply with the salt. But there's a degree of error that I'm not necessarily comfortable with study on what percentage of their actual body of literature in nutrition science dedicated to this question of like measuring sodium accurately in people. But it is an important one. You'll see observational studies that suggest this kind of J-shaped curve where they'll say actually low sodium intake poses a risk for cardiovascular disease, as high does, but actually like this sweet spot in the middle. And you look at those studies and they're nearly all based off just single 24-hour collections. And then studies that use multiple 24-hour collections, you don't see that curve anymore. You basically see a linear increase in cardiovascular disease risk, particularly hypertension-related cardiovascular disease risk, with multiple 24-hour collections. But yeah, it's something that this study kind of left. I thought I'd find it in the supplementary data, and then I went through it and I was like, oh, this is annoying.
Alan, slight tangent. In those studies, do they also find that same curve with stomach cancer? Because I know sodium.
Yes.
Okay.
Yeah. And so people forget this. So certainly in the 60s and 70s, the strongest association for sodium for an adverse health outcome for salt intake was with stomach cancer, particularly in Japan. So people used to think, oh, the Japanese have really low rates of heart disease. Yeah, but they had really high rates of stroke and stomach cancer, which were related to absurdly high levels of salt intake in the 60s.
Well, that's because they pickle everything, right? And salt.
And soy sauce and so the condiments and sauces are salt-based preservatives, And so there was estimates in Japan in the early 50s that salt intake, particularly in rural areas, was like 28 grams a day. I mean, it's just like, how do you get to that level of intake? I don't know. But that's why that this study being conducted in China and having largely rural areas is also good, because there are overlaps in the diet pattern that would mean that this is a population with actually quite a habitually high salt intake, and quite prone to stroke.
Yeah, didn't they give like 20 grams in this, or didn't they like allot 20 grams per person per day?
Up to, yeah. And that was to be used in everything. It was to be used in like cooking. It was to be used in like, adding. But yeah, it worked out to 20 grams per person per day. I mean, which is huge. Even if,
of the cohort, 72% had had a stroke.
Right.
I mean, right. And they're only 65. It's not like,
Yeah. So this is one of the, and this relates to, we were talking about this with the plant-based study. So, it was, okay numbers, but, 289 incident cardiovascular disease. One of the most robust things about this study is just the sheer number of deaths. It's like a quarter of the whole study group died. So it's something that adds to the confidence in the findings with this, is like, the number of deaths. I mean, out of basically 2,100 people randomized, and you ultimately have, essentially like a quarter of the study group die, over time. So yeah, an enormous amount of death. And we're talking about mortality endpoints. And so one of the big kind of criticisms of nutrition science is it tends to be long-term cohort studies like we just looked at that will look at mortality outcomes. But it's unethical. If you know something about diet and disease, it's unethical. You're not going to get ethics approval to randomize people to a diet that might result in a higher risk of their death. So with most, or certainly many intervention studies, they're looking at intermediate risk factors. They're looking at, this is the impact of diet on hypertension. This is the impact of diet on cholesterol. And people have pushed back on that and said, well, yes, okay, this diet might reduce hypertension, but does it reduce, actual hard endpoints? And so this, one of the most robust things about this study is the fact that, over 4,000 people actually died, and it was a hard endpoint. So it's, and for 4,100 out of essentially 21,000 people is a lot of death. So yes, you're right. You're talking about a population that is at high risk of stroke, that does habitually have high salt intake. And I think that's one of the strengths of it. So one of the difficulties with nutrients is that adhering to drug trials, right? Like, if we're looking at a drug trial, it's really easy for biomedical trials to have huge numbers of people and to have a true placebo. Like they just give people cornstarch in a pill, right? Versus an active treatment. And you've got this very clear placebo treatment. But nutrients, there is no placebo for food unless you're doing a specific niche supplement trial. But let's say I'm even doing a supplement trial. Let's say I'm even doing an omega-3 fish oil trial, right? My control group might be getting a placebo, but they still have adequate levels of EPA and DHA or their deficiency. So you're talking about control groups who at least have adequate amounts of what you're giving the intervention group. So this is really tricky methodologically for nutrition research. And so one of the pitfalls then is you take a population that don't particularly have that low intake, but they don't particularly have that high intake, and then you change their diet by not really that much, and then you get these weak outcomes, or there's no difference between groups, and you're like, oh, this intervention isn't better than no intervention, and you're like, well, that may not actually be the right conclusion. And so, and this is one of the issues recently with, say, saturated fat, because most of the studies where people had really high intake were done a while ago, but you won't get ethical approval for that now. You won't be able to say, oh, we're going to feed this group 22% saturated fat in their diet, because an ethics committee would be like, no, you're going to follow them over 10 years and watch them have a heart attack. So with this study, a real positive is the fact that you were navigating the ethical issue by studying a population who already have, so that's how you get around the ethics factor. So if you were to do this in the States, you'd have to be like, well, we're going to take these people who have an average salt intake of 7-8 grams. Oh, you can't do that. But because they naturally have this diet, you're able to actually do this research. So it's a real benefit of this study is diet, or a population with a diet habitually high in sodium. So you navigate the ethical issue, and then you're looking at this intervention. You're doing biochemical assessments to make sure that there is actually a change in sodium and potassium intake and output. And you have a huge amount of depth to be able to kind of compare, you know, the lower sodium versus the normal sodium intake and see if there is a benefit to that intervention, in which case there obviously was. So I think that's an important kind of qualifier. Is there anything in the findings that people think are interesting? Let's share my screen again.
So the deaths, that 4,172, that was only the people in the control group. Is that correct?
No, there were deaths in both groups. So if we go down here, this was a really helpful way of portraying the data. So you can see the salt substitute group on the left and regular salt on the right. And then what they did was they compared the number of events per 1,000 person years. So here you can see basically 29 events per 1,000 person years in the salt substitute group, 33, nearly 34 in the regular salt group. And then comparing that, then you can see the relative risk here. So 0.86, so a 14% reduction in risk, and a confidence interval of 0.77 to 0.96. And comparing that to our last one, which was just this huge confidence interval, this is obviously like much tighter around the point estimate. So there's a lot more confidence in the precision of this outcome, and it just simply reflects the actual statistical power from the number of events. And then you can look down this, and it's quite interesting then, you know, so you've got, obviously then they've divided stroke into fatal, non-fatal, hemorrhagic, ischemic, undetermined, etc. And I think one of the really interesting things here is the hemorrhagic stroke. So why is anyway, I'm trying to highlight that, but you can see here for an event rate of 4.37 versus 6.3. And quite a strong, you know, like 31% relative risk reduction, and even tighter confidence intervals. I mean, this is 0.85 is the upper estimate, so it's even quite far away from no association. And the reason that's interesting is because it's consistent with the wider sodium reduction literature, is hemorrhagic stroke in particular tends to be reduced. And so I always think it's a way of reconciling any individual study is, where does this stack up with what we know? You know, is it consistent? Is there the same finding in different populations? And you would say, well, that's actually what we saw in Japan. They reduced hemorrhagic stroke. The EPIC cohort, which is this huge European cohort with 10 different countries all included, their studies have also shown decreased hemorrhagic stroke in different populations. So you're like, okay, this seems to be fairly consistent as an effect of this dietary change on this outcome. And that's always a positive then when you're thinking about across the population. You know, is this a consistent exposure kind of outcome? And then this, like vascular disease. So again, understanding what we know about the effect of sodium physiologically is on the vascular system. So the reduction in vascular cardiovascular disease, and the difference again is quite striking. You know, 22.9 per 1,000 person years, 26.3. So I think that's, you know, you can see where is the.
I have a question, Alan.
So yeah, here. Yeah, I was just going to highlight that here you can see the difference. So this is the salt substitute. You had 1,969 deaths, and then in the normal salt, 2,203. So you got deaths in both groups, and a lot of deaths in both groups, which again makes that comparison. If all the deaths were in one group, you wouldn't really have a meaningful comparison. So this is actually quite a useful, albeit, you know, touch wood, a lot of people died, but it's a really useful comparison because you're able to say, look, this relative equal amounts of so what's the risk of death in these groups? So who had a question?
Sorry. I had a question. Could you elaborate on the number of events per 1,000 person years? Why do they write it that way, or what does that even mean?
Yeah. So person years is a way of accounting for, like with this study, right, we have basically 5 years of the actual study period. But within the study, you could have someone who died after 1. You could have someone that died after 4. You could have someone that died after 5. And you could have someone that made it through the whole study and is fine. And so person years is a way of factoring in that each individual in the study may have been in the study for a different actual duration before an event happening. So you're able to then kind of like average out, you're able to kind of quantify things in person years, basically is like years in the study. And you're able to then use that to represent like the entire study. So it's a way of kind of standardizing the fact that one person may have died after 1 year and one person may have died after 4, for example. And then you're able to represent if in a hypothetical scenario, in a statistical scenario, if I was in the study for 1,000 years, you know, 1,000, how many people would die basically within that? So that's what that metric is representing. It's a useful way of standardizing, you know, the time in the study, factoring in that people may have been in it for a different period of time before an event or before the end of the study, or even indeed before just dropping out, for example. Does that make sense? Yeah. So it's actually it's quite a useful metric then, because you're able to think about risk in a way that I don't know. I find people kind of are able to engage with the difference in risk in person years. When you get the number like 29 versus 33, like that suddenly starts to become okay, that there is a difference here. You know, and it's a way to then think about the relevance of this across the whole population, because one of the big is it a misinterpretation or just maybe a misunderstanding, particularly when it comes to interpreting like observational research, is people will say, well, the absolute difference in risk is only like, you know, 2 diagnoses per. I saw someone kind of make this argument in relation to processed red meat and colorectal cancer, and they said, well, you know, the difference is like 3 in 1,000 people. And I said, okay, yes. And so for an individual risk assessment, if I'm thinking about me and I'm saying, well, my diet's pretty good. I eat a lot of fiber. I have all these other things that are beneficial, particularly for colorectal cancer risk. I'm not going to freak out if I have a bacon sandwich once a week, right? But that's not how we're generally thinking about those findings. We're thinking about population health. So if you think that the difference is 3 diagnoses per 1,000 person years, as an example of something people would say, oh, it's not a big deal. Well, then scale that up to the whole population. Like, what's the population of the States right now? 430 million. Population of the UK, what, 67 million? It's a lot of thousands. That's suddenly a lot of people. That would be a difference in a diagnosis. So you're thinking about how do we shift this risk across the whole population to get more people away from higher risk to lower risk? And that's where those statistics become meaningful. But they can sometimes lose their meaning if you try and think of it too individualistically. So for something like this, go on.
Why don't studies do like, what is it called? Natural frequencies, right? So that you can get a broader scale instead of saying, here's a relative risk to this group or an absolute risk for this. But if we broke it out in a natural frequency, that's kind of utilizing that larger group statistic for, okay, in the United States, I'm going to use 300 million just because it's nice, right? If we got 3, now I have, that's X many, thousands or whatever it is. We got 3 per 1,000. So we've got, I'm going to say 30 million times 3 is 90 million people that are there. So here's kind of a more natural frequency, right? And if you actually do the charts and break it down, it gives you a nice relative number so that you can actually compare things to things. Because a lot of times, if you're talking apples and oranges, if we just give them a bigger scale, it might help people understand those things a little bit differently.
Yeah. I would like to see researchers do that more. There was a famous epidemiologist in the work through the kind of 70s and 80s called Jeffrey Rose, and he was really good at illustrating. He would have 2 bell curves, and he'd be like, right, here's a bell curve of high risk, and here's what happens when we change this exposure. And you visually see the bell curve like shifting from like right to left. It's like, that's quite powerful for people to be like, oh, okay, now I get it, right? And yeah, I don't know why it's not done more often. I would like to see researchers better articulate their conclusions as far as risk goes. I think we'd have way less like misinterpretation, particularly now that everyone's like posting on, study findings on Twitter or social media. It's just like, I think if the authors themselves better communicated risk, we might be left without people having to come in after the fact being like, wait, this is what this actually means. So yeah, I think it's just probably laziness, really, or publishers just being like, nah, we're not going to make you do it. So but this is like with this paper, so this is an example again, this is New England Journal of Medicine, right? So if you come down, what they really did with this, now it wasn't necessarily at the risk level, but they actually quantified the economic aspect of, what this would take, and the difference being per kilogram of the salt substitute was what, like 50 cents. So, at an economic cost, you're basically saying, actually, this is pretty cheap as a practical intervention, food-based intervention. And, they do this comparison with the modeling study here at the end. So they estimate 365,000 strokes, 461,000 premature deaths. So that I like that kind of articulation of like scaling this up to the whole population. This is what the finding in our study could translate into across the whole population. But you will not find that in every paper, but this is a really robust study in one of the best journals, possibly one of the best journals going. So they have this added level of like context that you wouldn't find in a lot of other papers. So that they have done it, but a lot, most papers probably won't. Anything else about this paper?
This was an interesting kind of look through the analysis, because this was their sensitivity analysis or their subgroup analysis, where you're saying, okay, like, does age affect it? Like, was there a difference in the finding between sex or more or less education or people with, you know, vascular disease already or anything like that? And you kind of see that most of these are fairly stacked up. You know, there was a slightly greater risk reduction in the over 65s, a slightly greater risk reduction in women compared to men, no difference in education, a slightly greater risk reduction in people without cerebrovascular disease at baseline. But the width of this here, you can see kind of slightly more imprecise. A slightly greater risk reduction in people with diabetes, slightly greater risk reduction in people without hypertension. But interestingly, no difference in whether they were using antihypertensive drugs or not. So I think these kind of charts in a table in a study like this are always kind of good to scrutinize, just to see were there any kind of major differences. And, you know, you could make the argument then that, okay, people over 65, female, you know, any of these kind of variables slightly benefit more. But overall, they're fairly well matched up right down this. And all of these are left of this line, the 1.0 line that we discussed before. So, you know, this side, right side of this line favors the regular salt, the left side favors the salt substitute, and they're all pretty much stacked up here. So across the board, for the most part, independent of these variables, that there was a benefit to the salt substitution. Yeah. Anything else? From this study in particular?
What level of interplay is there between the potassium that they substituted and the sodium, right? So what's driving that change? Can we say it's fully that reduction in the sodium reduction, or is it the interplay of sodium potassium and they're getting more potassium as well? So now we're having a different mix in the water, so to speak. Do we know that, or is there ways to look at that?
There are a number of ways to think about this. One is the difference between a confounder, like the smoking coffee example, and an effect modifier or a moderating factor. And so the difference is that you might have something like sodium and heart disease, right? Where because of the impact of sodium on hypertension, on left ventricular mass, on other aspects of vascular function, that these are adverse effects for the most part when you know, in consumed at high levels over time. Potassium is generally then considered the kind of yin to that yang, right? So it's associated with kind of oppositional effects for the most part. The difference is that potassium on its own doesn't increase your risk for cardiovascular disease. So it's not causally related to cardiovascular disease in the way that sodium is. So what potassium is not a confounder, but it modifies the effect of sodium. So it doesn't invalidate that a relationship still exists between sodium and heart disease, or, you know, the processes that increase risk of heart disease, but it does attenuate the size of the effect. And the reason that's important is because we have analyses that have looked at, and it is very common where people will say, well, hang on a minute, you know, it's probably just a benefit of potassium. But actually, the studies that have looked at this in relation to cardiovascular disease have found that the strongest relationship with potassium, with higher potassium levels, and so a benefit to potassium, is actually when sodium intake is also low. But if you have high potassium intake and also really high sodium intake, there's still a relationship. So potassium doesn't have the capacity to completely just invalidate the effect of sodium. So the benefit of potassium is primarily observed when sodium is also low. And so that means that really, for the most part, although certainly potassium, like, you know, is likely to have played a role in this, but the primary change
is still related to the 25% difference in sodium between the regular salt and the potassium enriched salt, or the salt substitute. So I think thinking about things as effect modifiers rather than potential confounders is one level. And we could see this. We could see the same with the dietary fat and heart disease research, right? We could see the same with, say, saturated fat, and then you take unsaturated fat, and we know that they'll modify the strength of any association between saturated fat and heart disease. So that, I think that thinking of potassium as an effect modifier and understanding that the kind of wider research suggests that the main benefit of potassium is observed when sodium is also low, but high potassium isn't a license to go having 20 grams of salt a day. It won't just abolish the effect at that point. And we actually see that in the studies that have looked at populations living fairly kind of traditional lifestyles, still like not touched by modernity or kind of living in urban environments, is you see they have quite high potassium intakes, but their sodium intakes, their salt intakes is like 1 gram a day, 2 grams a day. So there is a benefit to the potassium, but it's not going to invalidate the effect of sodium at higher levels on, hypertension and heart disease risk, if that makes sense.
Logan,
awesome.
He left, but one of the guys that was on here was like, these studies are way more complex than most of the studies we've been looking at. I think it's because they're fucking giant, and kind of what like Paul alluded to, so much of the literature that we're seeing is just like, 20 people in each group, and making broad conclusions is not possible. Whereas here, like this has, potentially massive effects on, population-wide groups.
Yeah. And it's also that nutrition is just a really hard science, like it is a really difficult science to do well. We've also been stuck with this assumption from the biomedical realm that they just expect that we're able to do studies in nutrition like we're doing a drug RCT, and they expect us to get the same outcomes, and then we don't, and they're all like, nutrition science really reliable. It's like, no, but you can't make us do research according to the way you do research and expect to get the same results, right? So it's just a complicated science as well, in and of itself, and it's difficult to do to those kind of biomedical stuff. Like you can't double blind every nutrition study. Like a participant needs to know they're taking a pill, or that they're drinking olive oil, or like how do you blind them to their daily life, right? So yeah, it's a complicated kind of science, and it's one that's quite difficult to do well. And then I think if you add in the fact that what you're describing, if you're used to looking at kind of small, very specific studies, like in small sample sizes, then you're suddenly coming across a study with like 20 to 30,000 people, or even more. Like I've seen analyses with like nearly half a million participants. Like it's an absurd amount of people, but it's great because you've got this wealth of data, and the more data you have, the more likely you are to find something that's meaningful.
Go ahead, Chris.
I was just going to say, yeah, I mean, it's very humbling looking at a different area of literature, because it's like, I mean, probably more than anyone that nutritional information is still all over the place, but you have these, huge population, or this huge subsets that you're studying, and it's way more nuanced, and there is funding looking at this, but then you have the groups that are just these, kind of like the quacks that you talked about. So it's still all over the place. And then with, like at least the MSK side, it's like, there's way less funding, there's way less like ability to do these types of studies than even with nutrition, that it's like we probably have even more craziness going on.
Right, right. Yeah. I think anytime you have an evidence base that is either, complex, has complexities, or requires subject specific matter knowledge, or, has like what you're describing, the kind of like smaller trials, and, I think there are areas that are just ripe for quackery, and people can kind of almost get away with saying whatever they like because they can say, oh, well, this study showed that. And it's like, well, it's not whether the study showed that or not. It's whether the study's like methodological rigor allows them to make those conclusions. But of course, quacks aren't interested in that. They're just interested in, this confirms my bias, and off they go, taking to the internet. So yeah, I think there are certain fields that are a bit more prone to that kind of quackery, really. Nutrition.
I would say anything that has to do with public, though. I mean, honestly, because the public has such a low level of education of this. If I say this article says that, well, it was published in a journal, therefore they don't understand that there's journals that you just pay to publish in, and they'll publish any piece of shit that's out there. And so and on one of your things, you say most of what this guy's published is commentaries or editorial stuff, right? But he talks about his pubs that are in certain journals of repute, but all he's doing is writing a commentary on some shit. It's not like he's actually published good literature. So when you're talking about that, it sounds like these people, and everybody goes, oh, you're talking science? I don't have a good background in that, much less research, methodological. I mean, hell, we're confused with the statistical analysis here, right? Imagine what the general lay population is looking at, and they're like, all right, whatever he says. So it's just so much easier to trick the populace, simply because there's so much shit that can be put out, and I now have a publication, right? I now have this. And so it's very confusing to be a general populace, because you have to go read, and how much, I know in our world, it's every day there's 1,000 new journal, articles being published. Most of them aren't worth shit, but they're being published, right? I know that's in yours. And so how the hell are people even supposed to keep up that are in the fields, much less the lay population? And then we put trust in these people. I wrote a book.
Exactly.
And now I'm going to put my book from now on, and that's going to get it, right? I mean, it's that kind of stuff.
Yeah, I get emails to my academic email all the time being like, hello, sir, we are like, and it's just some random ass journal title, and they're like asking for a paper, and I'm just like, this is predatory, it's absolutely, and that's, and I think, with the information age as well, it kind of combines with this idea of like, people love the idea of being self-taught, and, I've done my own research, and that lends its own problems to the whole mix. And it's difficult. I don't think there's an easy answer to any of it, to be honest, other than the publishing world really becoming a lot more, rigorous with identifying, predatory journals, or, just, I think academia needs to police itself a bit better. I think it just lets a lot of shit slide. And I don't think that's helpful. I don't think it's good for public trust. I don't think it's good for science having transparency. So I think that academia could definitely do a better job of like policing itself.
How much do you think is publish or perish? I mean, because a lot of tenure, a lot of professors have to publish, right? If you're a tier 1 university, if you ain't publishing, you ain't going to get tenure, right? And so now I've just got to publish, whether it's even necessarily good, right? So this becomes almost where we put pressure on the university or on the staff to create stuff. So they're just creating shit, and that just puts a big shit pile. And now we're looking for the diamonds in that shit pile, right? To find it, rather than going, hey, look, as long as it's good research, take your time. You've been here a while. Your students like you. You're doing this. You've got grant money coming in. Here's your tenure. That's not how most of it works. My brother's a PhD in genetics, and that's just not how it works, right? I mean,
no. Yeah, I don't think publish or perish is serving academia well at all. Like, it's setting the wrong, tone across the whole of the academy, and it's setting this tone of like quantity over quality. Output is all that matters. It's any system like that is never going to, whether it's, whether it's like, corporate, like, interest or financial interest or academic, like any system like that is never going to work out well, because, the worst will rise to the top, unfortunately. So, yeah, I'd like to see that change. It's shifting a little bit here. Definitely, like there's less onus on publishing and more on actually kind of bigger grants that produce more quality research. So I hope that spreads. I hope that becomes the norm.
Yeah, y'all have better funding over there, because I mean, the National Science Foundation, some of that stuff, that grant money's dwindling, and so now you're fighting over fewer and fewer dollars to make big grants, right? So
yeah, it's the funding is, they're European bodies that the UK is probably going to lose out on now because of Brexit, and then there is good funding, but like there's only ever a finite pot, and because of COVID, immunology, all of these kind of fields are getting the preference, and I think there's going to be a few fields fighting over whatever scraps we get from immunology and virology and vaccinology and all of these kind of areas. So yeah, we'll see what's there.
All right, we can cut it here. Alan, I appreciate you, being able to come on a Saturday afternoon your time and chat, and very different journal club than what normally we have, but I very much enjoyed it because most of these are just very like, I want to say comfortable, but very like, self like bias inducing. And it's like, I know very little about this type of research. I haven't looked at it. I haven't looked at this type of these stats, so I'm glad we were able to dive into something that like made me uncomfortable.
Great, yeah, that's always good. It's I'm really happy to do it, and thanks for everyone for kind of engaging and making it like interactive and fun. And yeah, like if you guys want to do it again at some point in the future, more than happy to. Let me know.
Man, I appreciate it. Well, enjoy the rest of your weekend.
Awesome.
All right.
Yeah, you too, lads. Take care.
Bye.